Tom says the following. Look back at the part 1 table and complete 3 mathematical verifications. Okay, we're going to look at A, meaning part A from the table, part B1 from the table, and part B2 from the table, I think, if I'm correct. Now, it says, use the value of theta that you determined as the launch angle in part 1. In part 1. So, for part 1, if we're looking at part 1A right here, what was the launch angle that most people got? 43. What else? What did you get? Look at your table, please. What did you get for theta for part A in table 1? 45, 45, 43, 45. Okay, the angle traditionally for max range is 45. So if you got 43, please leave it though. Don't change it. Use the angle you got. But just so you know, test question, just so you know, make sure you know that the optimal angle is 45 degrees. That is what really gives you the maximum range without air resistance. With air resistance, it changes. Okay? We can't actually come up with an angle for that depending on the air. We have to know more about the air. So, let's use theta equal to 45. Now it says to find 3 things. And these 3 things you found on the computer using the lab program. So we are finding them mathematically, and we're going to verify that they were correct in our lab. So you are not using any more lab data at this point. Is that clear? You are given everything already here in this problem. Do not go back and use time or x or y, because that's what we're trying to figure out. So we want to figure out those 3 values. So let's start by making an xy column, please. In the x direction for this first part, we don't know what x is. We're trying to determine it. So we'll put a question mark there. We don't know what the time is. We're trying to determine it. We'll put a question mark there. We do know the initial velocity in the x. What is the initial velocity in the x direction going to be? What is it?
20 times cosine. It's always 20.
Again, launched at an angle, so it's 20 cosine 45. Remember, look up please. 20 is only the VI, not VIX. VIX is whatever VI is times the cosine of the angle. Same as last problem. Let's move over to the y direction. We don't know the y at max height. I'm going to put y max to specify. Okay? We're trying to find y at max height. We don't know... Well, we know the acceleration in the y direction. What is that? Okay. And what is the velocity in the y direction?
20 meters per second.
Times?
Sine.
Yeah. Which happens to be the same thing as the x direction. 45 is when they're equal. We also don't know the time. Now here's the weird part. Ready? Watch this. In the y direction, we really want to find the time to max height, or the time for the whole thing, or the time, it takes to get up there. It's not the same as the time on the x direction. How are they different from each other? Give me a relative value of each other. For example, the time it takes to get, watch me, the time it takes to get to max height is blank the time it takes to get the full way. Half. So if we can determine the time it takes to get to max height in the y direction, what can I do with that number then? Yeah, double it and bring it over here to the x direction. So this is why it's a little tricky. Now the next part is this. Notice when we're at max height, what happens for a moment in time at max height?
There's no VI.
There's no Vy. Let's use the term Vy. No velocity in the y direction. Watch me, ready? Here we go. Rocket gets launched. It gets launched. It gets launched. It gets to its max height. It's still getting higher. It stops. And then what happens? It starts to fall down. It's always moving in the x direction. Even when it stops at the top vertically, it's still moving in the x direction. Because ax is 0. There's no acceleration in the x direction. So it's never going to stop moving in the x direction. But it does have vertical velocity until it gets to the top, and then it starts to fall back down. So at max height, Vf could be 0 in the y direction. So here's what we have to write here. And that's the key to solving these problems. Without doing that, you cannot solve it. Because now you can use an easier equation. You don't have to use the equation we've been using all along in the y direction. There's an equation that is much easier, that relates the last four variables.
Wait, that sounds supposed to be.
Is that VTY?
No, is that theta equals VFY equals 0, or is that just in the variables?
No, that's just carrying down. This is the second problem, Mike.
Oh.
You see what I'm saying?
Yeah. No, I just wondered.
No, ignore this stuff down here. This is the second problem. You're going to do the same process there. Again, at max height, it pauses momentarily in the vertical direction. It stops gaining height and then it starts to lose height. So your vertical velocity must be 0 when you're at max height. And since we're looking for the time at max height, we can use the last four variables. Ignore y max for a moment, please. Ignore y max for a moment. Look at the last four variables here. You've got VF, VI, A, and T. So use VF equals VI plus AT. Use that formula.
Wait, but we don't have T.
You're looking for T, Mike.
Oh, okay.
So look at the top of the board. It's all in the y direction. So we should specify by putting little y's here. Okay, VF in the y direction, we just said, is 0. I'm just going to plug in numbers. I know we can solve, just to make it easier. 20 times sine of 45. Is that 17.68? Was that the one from last time? 14 point?
It's 14.1.
Okay, so that's your equation. 0 equals 14.1 plus negative 9.81, or just minus, I guess, t. Solve for your time, you get. You got the time?
No, I was going to subtract 14.1.
And then divide by?
And then divide by negative 9.81, so you get negative 14.1 over negative 9.81.
Two negatives make up?
Positive.
Perfect. What do you get? What's the number? Who's got it? Phil.
1.44 seconds.
So that's the time it takes to get to the max height in this problem. The maximum height. Is that clear?
Yeah.
Now, that's not the time we're looking for, though, in the beginning. It said find t. That's the whole time. So what should I do to that number? Yeah. So 2.88, put that over here in the x direction now. That's the time for the entire flight. And if you go back to your lab, your time for this was 3. Most of you had 3 for your time. 2.88, approximately equal to the answer that we got in the lab. If you go to your lab, table 1, part A, most of you wrote down, I think, 3 for your time.
Yeah.
3, maybe 4. Did anyone write down 4 for this? I think it was 3. Come here.
Wait, how did you get 1.44?
By solving this above equation here. Subtract 14.1, divide by negative 9.81. Solve for t. Right? Come on, you can do that. It's only one variable, one equation. You can do it. Now, we've got the time it takes. We want the x, or the range, right? The range, the x, the horizontal displacement. We know everything in the x direction. Solve for x. What equation am I going to use?
VIX times t equals x, or VIX over x divided
Yeah.
by t, and then you would change it into...
Good, Mike. You're really picking up on this really well. Mike already said, just move the t up. He did it in his head. He said VIX times t equals x. That's exactly right. So move the t up, and we get VIX times t equals x. So I'm kind of moving up here to keep on the same page, all right? So that's what we end up getting. So take your VIX, which is the same number, 14.1, multiplied by 2.88. It's many. 40.6. Go back to your table. See what you wrote down for the maximum range obtained. I think some of you got like 41 or something, or 42.
42.
42, Mike? Okay. 42. Now, the one thing I want you to notice is that in your lab, remember the football kind of ends up below ground level at the very end? Do you remember that or no? Anybody's noticed that? Watch. Look at my hand. The ball was launched and it kind of landed a little bit below ground level, if you remember from the lab. That little extra x that you're seeing here, we're getting 40.6, you guys got 42. That's 1.4 meters. That's that difference. When it goes a little bit further, that's that extra x there. Okay? So that's where that's really coming from there. Anyhow, with that said, that gives us the x value. The last thing we want to find is the y at max height. Look in the y direction. What equation involves y? What equation involves y?
The one that we always use, y equals velocity initial y times time plus 1/2 acceleration time squared.
Good. Or, technically speaking, right? Doesn't that work also, Phil? Take a look at the bottom one I just wrote.
Yeah, that works also.
It works also. They both solve for y. Now, if we use the first equation, VI is still 14.1. What time would I use? What time would I use?
You would use the 1.4 to the max height.
You would use the 1.44, because that's the time it takes to get to max height, if you were using this equation. If you're using the second equation, you set VFY equal to 0 again, because it pauses at the top. Set VFY equal to 14.1, A is still negative 9.81, solve for y. Either way, you'll get your max height. Some of you got like 11, I think, or something like that for max height in the lab. Was it like 11 meters or something?
Yeah.
Table 1. This will help you guys on one or two of the problem set problems. What we just did here with the max height. It's on, I think, 2 of the problem sets. Okay?